Hi everyone. So we managed to derive the work done under a constant pressure process. Okay, as you can see in the PV curve. Okay, the work done is actually the area under the process. So actually this can be applied for all the other processes as well. Okay, and the approach will still be the integration of the pressure with respect to volume from state 1 to state 2, okay, from initial to final, not from small to big. Okay, if your process is from a big volume to a small volume, the integration should go to the left, and in fact this will cause your result to be a negative area, which is actually true. Means because you go from a big volume to a small volume, you're actually compressing the gas, and the work done is not done by the gas. It is work done on the gas, and the work will be a negative value. Alright, so we will show that later on, but let's just look at another process, and that is the constant temperature process. Okay, how does a constant temperature process look like in the PV curve? In the PV graph, you know that PV equals to mRT, right? So if temperature is constant, so this T is actually constant, and we know that if we look at a closed system, the mass doesn't change, the gas constant also doesn't change. So this whole term on the right side, mRT, is actually constant. Okay, so in fact if we replace it by a letter C, constant, okay, and P actually becomes C over V. Okay, if this is the y-axis and V is the x-axis, this is actually a inverse function. Okay, it is something like y equals to 1 over x. You're actually plotting something like this. Okay, and the shape of this inverse function will be like this. Okay, will be like this. So the same, let's say this is V1, this is V2. So state 1 is here, state 2 is here. The process goes from left to right, and as you know it, the work that is done is the area under the constant temperature curve. Okay, so work done is integration of P dV from state 1 to state 2. And PV equals mRT. We're going to use this again, and this one will give you P equals to mRT over V dV. Okay, and you also know that mRT is constant, right? So it can be taken out of the integration. 1 to 2, you are integrating the inverse of V with respect to a V. Okay, and this one will actually give you a natural log. Okay, so you are actually natural log of final minus natural log of initial. Okay, and by the logarithmic rules, we can actually combine this to become natural log of V2 over V1. Okay, and this term, okay, and can also be replaced by a PV. Okay, so because PV equals to mRT, so it can be also expressed as PV. Just that when you use PV, you have to use the same state, P1 V1. Okay, and then in that case it will be ln V2 over V1, or P2 V2 ln V2 over V1. Okay, so this is how you derive the area under the constant temperature curve.